We're about to do a live, and tonight Baji Baba has a lot of physics to cover with you. Tonight, Mama has made her tea and getting a snack ready, and hopefully seeing many of you joining on this live. Baji! Baji Baba was busy playing with his siblings. We were just all playing. Here's Sachi. She is drinking water after jumping around quite a bit. And Baji is over here, and he has claimed the box. I hope that I see many of you joining tonight. Hi, Baji. Say hi. Hi. Let me see that all the settings are set. I've got the light on. I've got all the things. If you are joining, here is my tea, by the way. I think it looks gorgeous. I just made a chai latte for myself before I get started with the live, and it looks like this. And I think it's quite nice. And here is the Nido container for the phone stand here that I will be using for perusing for as a phone stand. And there is my kitchen. Oh my gosh, this tastes very good indeed. It's a masala chai latte that I got from the store near me. And here is my here is my snack as well. So tonight, hopefully I see many of you and we will be covering some physics as usual. And hope to see you soon. Hello, hello, hello. I am here. Hello. And so is my snack. Let's see what this snack is like. It's called Chobani. Oh, I see. Cookie dough and yogurt, where I can put some of this into here and eat that. I see what's going on. I wasn't entirely sure how that would work. I got it from Aldi. Hello. If you're joining, please say hi in the chat. And we can start shouting you out. We can say hi to you in the chat and call out your names and things like that. Okay. Let me fix my hair here. Hello, how are you doing? Hi, cool boy. What a nice username. Baji and Suji are fighting over there. We're going to be using the same book as last time, by the way. And let me get started. This is a Greek yogurt with cookie dough on the side. And this is a masala chai latte that I just made for myself. Welcome, welcome everybody. Thank you for joining. Let me fix the angle of this thing. I think that's probably fine. I went swimming and now here I am to go live with you guys. And we're going to study physics. And we're going to say hi. Hello, cool boy. Ashraf, hello, how are you? Ashraf Gujarati is saying, where are you from? Cool boy is saying, I'm okay, watch it eating. Well, this is Chobani. Can you see? This is a Chobani snack, Greek yogurt container. And do you like Chobani? Hi, Joe Dirt. Hi, Angelica. Angelica Marie is saying hi. Uncle Shu is saying hi. Electric is saying hi. Joe Dirt is saying, I also love you. Well, thank you so much, Joe Dirt. Everybody, please do join in on the chat as we get settled here. And we will call out the usernames. We will give you some shout outs and we will pin the book. Fuji! Fuji Baba is crying. Thank you, universe. Thank you, God. Evil eye remove and touch word. We must thank the universe for keeping all the evil out of here. Thank you, Uncle Shoefly. Shoefly. I hope I'm not saying a bad word. Thank you, Joe Dirt. Thank you, Electric. I love her more. Oh, how sweet. Hello, Uncle. Thank you for the floating heart. Angelica Marie Salinas Navarro. Hello, my darling. How are you doing? We will certainly say hi to everybody. And last time when I tried to log into my YouTube live and change the settings, it was a little tumultuous. I hope that this time that is not the case. Oh, please do like, share, and subscribe. I hope you're doing that, guys. I really need it. Hello, Shakta108. Hello. Hello, Shakta. Hello, Electric. Hello, Gabrielle. Wow, how beautiful, my angel. Oh, hello. Hello from your angel. Can we get 10 likes? Hello, Mike Hunt. Hello, JD. It's 12:18 in the morning. Um, as far as I can tell, Eastern Standard Time. What do Gabrielle is saying very cute. Hello. Hi, Whoop-de-doo. My goodness, Whoop-de is here with a doo-doo. Hello, visible personage. What do you do here? I teach physics, cosmology, astronomy, and astrophysics. You should tune in and you should stay tuned in and you should like and subscribe, my darling. Angelica is saying, what were you born? But I was born in 2021. Oh, my dear. Well, I'm glad you were born. Gabrielle is saying, let's get married. Well, thank you so much, Gabrielle, for being here. Hello, Kelly. Cool. Do you like stray kids? I like stray kids that are cats. Indeed, I do. Really, I enjoy physics too. Hello, Shakta. What is the theory of relativity? Actually, that's a great question that you asked because tonight I think we will cover some gravitational lensing, okay? We have been covering cosmology quite a bit lately. We talked about the universe, the evolution of the universe from a baby stage to the way it is now. Some relativity. And right now, we will get into some of the technicalities and talk about gravitational lensing, okay? So I hope you're here for that. And I hope that you stay tuned. And can you subscribe? Can you please subscribe, my darlings? Are we ever going to understand black holes? I mean, we understand black holes to a large extent. We've done a good job since over 100 years ago. When black holes were actually classically theorized. So, from general theory of relativity, we actually knew that black holes can exist. And, because general theory of relativity gives us a theory for gravitation, and black holes are basically the most extreme case of gravitation, and also includes um, a point of singularity, classically speaking, just like the Big Bang, but kind of in the opposite direction, where you know. So, so this sort of this infinite density or infinite gravitation that is a black hole was actually something that we already knew about theoretically from the general theory of relativity. And Schwarzschild did a great job of, basically solving the equations of relativity and giving us the equations classically for black holes, giving us something like the Schwarzschild radius. So Schwarzschild is a person, a bit tough of a, you know, tough to spell last name, has a lot of C's and S's and Z's and whatnot. But I know that it ends with a child, so Child. So at least I can get that part right mostly. And the first part is Schwarz, maybe, and then Child, Schwarzschild. But please do look it up because I probably misspelled it here and there. So this person actually gave us a way to theorize and understand black holes using the equations quite simply. And he gave us the Schwarzschild, like basically the black hole's radius. There's a formula for it. It's called the Schwarzschild radius, and it all comes from that work, which of course is based on general theory of relativity. Okay, so in that sense, black holes were theorized over 100 years ago, and we kind of knew about them. But what people thought back then was that these were quite extreme types of events or objects, not really events, more like a phenomena or objects, right? So people thought that they probably don't exist. Like um, they were not expecting for them to be real, but they did have a way to describe black holes. Okay, but then of course some of the theoreticians did indeed want them to be real, and they were kind of hoping that these things were real. And then lo and behold, when neutron stars or pulsars were discovered for the first time, and that I'm forgetting the year, um it was much later. Actually, it was, I believe the person's name was Jocelyn. Let me just look it up really quickly. This person, a graduate student, a woman, she was looking up at the sky and observing things, and came upon, she accidentally and brilliantly um, discovered pulsars. And that's how we got these extremely compact objects that are not as compact as black holes, but they are quite compact, very extremely compact. They have about a 10-kilometer, here it is, Jocelyn Bell Burnell. They have about a 10-kilometer radius. So, something that comes from a star and has reduced down in size to a 10-kilometer radius is a very compact object. So that's a neutron star. And I mean, they're also known as pulsars because many of them, if not all of them, basically have the pulsar um, attribute. Okay, so yeah, I'm telling you this answer in a lot of detail now. Somebody asked about black holes, and now I'm telling you about neutron stars because it's important. It is extremely important, and it was extremely encouraging to people when the neutron star was discovered. So let's read about Jocelyn Bell real quick, okay? Because this is an extraordinary person and grad student of her time back in the 1940s. Well, actually, she might have been, it might have been 1950s when she actually discovered this, but um, back in the 1900s, this person made a very, what do you call, very extraordinary discovery. Okay, and it's quite, encouraging and inspiring. So, Jocelyn Bell Burnell. Wait, is she still alive? We should look it up. We should look it up. But anyway, 1943, she was born. British astrophysicist Jocelyn Bell Burnell began focusing on radio telescopes early in her career. Originally from Northern Ireland, Bell Burnell studied initially at the University of Glasgow in Scotland. After receiving her PhD from the University of Cambridge, she worked at institutions in the UK and abroad, including Open University. Bell Burnell focused much of her research attention on quasars. So we've also talked about quasars. This is a type of galaxy. In fact, this is quite a, oh, she's still alive. Oh, oh my God. Thank you so much, MYKE, Mikey. Thank you so much. Oh, that is great news. That's great news. I didn't know actually. I mean, she's such a big figure. I thought of her, I mean, she's a historical figure, but maybe that's great to know that she's still alive. Wow. So, so she was actually studying, I mean, she was doing the radio astronomy, and actually there's a whole story about quasars too. I don't want to get started on that because that's a whole nother story. And that's actually a very awesome story as well in astronomy, how quasars were discovered for the first time. And it's, in radio, and people thought they were point-like objects or stars, really, and that's why they're called quasars, quasi-star, quasi-stellar. Anyway, I digress. So I find all of these topics extremely exciting, and so definitely I am telling you all about it. So she was trying to work on that. She was a grad student. Okay. These are celestial objects. So this is quasars. Okay. These are what she was working on. These are celestial objects such as black holes that emit. So these are actually galaxies. So I don't know if I like that sentence too much, but because quasars are actually a type of active galaxy, they have, of course, a very active galactic nucleus. But they're actually a galaxy. Anyway, they were really new back then. So she was in the process of studying that. So then, in the process of studying quasars, she actually chanced upon pulsars. So she traced their patterns and located their source as neutron stars. So she, saw these pulsars, and pulsars are called sort of like clocks in the sky because the pulsar period, like literally like the period at which you will see them, pulsing at you if you're, in view of one, is so accurate, like it's so precise, like it's like exactly that one, so hello, everybody. I will say hi to you all and read your names in just a minute. Hi, Francis. Hello, hello, hello. So she looked at these things, and they turned out to be neutron stars, and they were pulsars as well. This discovery of a new classification of astronomical object, later dubbed pulsars, was one of her most well-known contributions to astrophysics. So she became really famous. Uh, Period as in the period of pulsing. But yes, the menstrual cycle also has a period, more like 28 to 31 days. But these things have a period of maybe, I don't know, very short. Like it could be like less than a second, it could be even shorter. Okay. So, all great questions. So that is Jocelyn Bell Burnell in the 1940s and 1950s. Okay. So now, why did I tell you all this about pulsars? Why did I do that? It is because when they discovered neutron stars that happened to be the pulsars that she discovered, hmm, let's look up the year she discovered pulsars. Um, was it the 1950s or 60s? Ooh, 67. Okay. Dame Jocelyn Bell Burnell is a Northern Irish astrophysicist who discovered the first radio pulsars in 1967. So in 1967, when she first discovered pulsars, which happen to be neutron stars, which is a stellar remnant, as in a star has died and compressed itself down to a neutron star, which is a 10-kilometer radius compact object, which is quite a drastic, um, what do you call? Compactification, compression, reduction of size down, from a much bigger object, which is a star. And basically an example of extreme gravitation, where the star was a really large mass star, one of the larger mass stars, not the largest mass stars, but one of the larger ones. And when it dies, when it runs out of fuel, in its collapse under gravitation, it has become a neutron star. So a neutron star is one of the more extreme examples of gravitational collapse. Now, the nice thing about discovering neutron stars, as far as black holes are concerned, which is what somebody asked me about, and I think they were asking about uh, when are we going to know more about them, etc. Well, black holes now became more of a reality because people were like, well, if something as extraordinary and extreme as neutron stars can exist, maybe black holes exist too, because they were even more extreme example of collapse under gravitation for a star. And lo and behold, actually, that was proved right. And black holes do indeed exist. These are, thank you so much. Hi, El Hode. Hello. These are some of the most extreme uh, mass stars that, when they die, will undergo some of the most, if not the most, extreme kind of gravitational collapse, leading to black hole. Okay, so we have come a long way since first predicting black holes over 100 years ago. And so that was my response to the question somebody asked. Okay, I got very excited because it's a it's an excellent topic for you to ask about. Okay, so now let me do my settings for my live because I never get to it usually. It's all messed up. Thank you for being here, Black Holes. Hello. Hi, Lauren. Hello, El Hode. Hello, Tame Me. Hello, Mr. Drew. Hello, El Sue. Hello, Terriel. Black hole of a galaxy, yes. So when I was mentioning about quasars are actually an active galaxy, as in they have a very active center of the galaxy, and they're sometimes called active galactic nuclei or active galactic nucleus. And pretty much, AGNs, active galactic nuclei, there are like three types of them, and quasar is one of them. So quasar is has a very active center, like basically a supermassive black hole, which is constantly gobbling up more mass from around it, and it becomes like this center of such huge activity that is pretty much contributing to the majority of the luminosity for that galaxy. So from a distance, a quasar kind of looks like a star because really you're looking at the luminosity from its center. So that can lead people to think that's kind of like a star. But the spectrum of a quasar showed that, well, this can't, this would be really weird if this was a star, and so on and so forth. And we've actually covered it in the past in one of the lives, in many, probably several lives, that quasars were very confusing, but they figured it out, and they realized, oh my gosh, well, this is just a very special galaxy. Okay, or a galaxy that we were not uh familiar with at that time. So that is what Jocelyn Bell was trying to study when she chanced upon this other exciting object or interesting object called neutron stars. Okay, and we can certainly talk about that more as well. Hi, Jayanto. I said I downloaded your picture. Oh, hello. You are so damn cute when you're smart. Oh, hello, Mr. Drew. Hello, Tame. Hello, neighbor. Um, hello, the bike. Hello, real squirrel. My ADHD denies such input. Why does my... Hello, Flips. Hello, Vicky. We are Stardust. We are golden. I love that. Hello, squirrel. Hello, Vicky. I'm still mean to you, Mr. Drew. Well, you should do a super chat. Been a while. Oh, hi, Francis. So, Francis Tremblay, how are you doing? Thank you so much for moderating. Hello, Mr. Eternal. Thank you. Hi, Angelica. See, I'm not the only one that was wondering if you were. Oh, hello, Slam. How are you doing? I like your accent. I'm from India. Hello, Realchair. Hi, Amit Grill or Amit T. Gill. Really good way to learn. It's a big study group. Yes, it's a big study group. You can ask your questions on astronomy, astrophysics, cosmology, and physics. I have a dog. His name is Chocolate. Aw. Hi, Mikey. Hi, Snapshot. Thank you. Hi, Natrona. Hello, neighborhood. Mr. Drew, you're still a little interesting, but you should definitely do a super chat. Thank you so much. Hi, Mike664 is saying finally some intellectual content. Thank you for the in-depth answer. I'm listening. Thank you, Mikey. You should subscribe. Um, Hi, Mr. Handsome. Hi, Angelica. Hi, John Doe. Hi, Nate. Nate. Okay. Hi, Slam. Hi, John Doe. Hi, V-Town. Hi, neighborhood. I think I've said hi to everybody, but if I missed you, please just message again. As in put something in the chat. Depends on the context of the debate, I suppose. Hello, Visible. Hello, Alex MC. Hi, David Sanchez. I can already tell you rarely lose debates. Thank you. Liked for you. You seem very intelligent. Oh, thank you, Mr. Or Visible Personage. Thank you. Are we ever going to understand black holes? That was the question. Yes. Love it. Well, we always try, and we've come a long way. That was sort of my response there. Thank you everybody for chatting and putting something in the chat. I really appreciate it. Mr. Drew, my goodness, you did do a super chat. Hi, Greasy Ronnie. Hi, Big Frank. Hi, Transmiss. So, 1 second, guys. I will come back to the chat. Oh my goodness. Francis, how many ear piercings do you have? Joydip Kosh, why do you want to know how many ear piercings I have? Hello, Joydip. Jeremy, did you do a gift, Jeremy? Thank you. Where's Acacio? I miss you, Acacio, if you see this later on. And Heike and Scott. If you see this later, I missed you a lot. And you should come to my lives or leave me a comment. And or leave me a comment or both. When you see my lives, by the way, guys, on YouTube, on my channel, wherever, you should definitely interact with it. My videos, my clips, my shorts, my lives, everything, interact with it and put a comment in, please. It really helps me. Thank you so much. I feel like the more reach my content gets, the better, because this is kind of a niche topic. So I appreciate your help with all that. I'll start a goal. Oh, I can see your comments on this side too. That is nice. Okay. Do you see the book that I have pinned? Can you see it? Oh no. There. Hopefully you can see it now. Sometimes it doesn't work right away. The book that I have been reading from, and I told you about Jocelyn Bell, that stuff. This book is now pinned, okay? Okay, that is not doing anything. Stream settings. All right. Thank you guys, everybody, so much. Thank you for liking the live. So, Jeremy is saying sent a gold coin for 10 jewels. Thank you. Aw, thank you so much. And thank you, Mr. Drew, for your super chat. Really appreciate it. Keep them coming. I made a goal. I think I saw another interesting question. What is your opinion on deep space organ harvesting? I don't know if I have one. That might be the first time I heard about that. I do kind of live under a rock though, so okay. Um, I pinned the message which is like and subscribe, please. Please do like and subscribe. Okay. Now I will read more of your comments because this has been nice to see your comments. Is this live? Yes. This is a live. This is indeed a live. And also, can you guys tell me if the audio is good, if there's no like static and stuff? So let's see. Hi, Mr. Drew. Harish Kumar. Hello. Hi, Harish. Arthur. Hello, Arthur. Maybe Arthur. Do you do any tricks? Hello, Eric. Hello, Lee Calling, Puerto Rican goddess. You're so pretty. Hello, Transmiss. Hello, Big Frank. Thank you for coming from Cleveland, Ohio. Hello, Angelica. I'm outside your window. Well, don't do that. Hello, Francis. I like and heart Mr. Drew's super chat. Hello, Tahat. Hello, Eric. Hello, Hussein. Do you like dogs or cats? I like both. I don't know why, but I prayed for you that you will have eternal peace. Oh, thank you so much, Leslie. Hello, Oddwood. Hello, pretty princess. Hello, John Francis. Good day. Johnny here from Australia. Well, welcome to Australia. You should like and subscribe. Thank you, Jeremy. Okay, so what's the next question that we're gonna tackle tonight? Hi, Ahmed. How are you? Interview, what's up? Finally caught up with you. Hello. Yes, I'm here. How are you doing? I don't know the first thing about astrophysics. Why should I get this book? That's a great reason to get the book. If you don't know this, don't know anything about astrophysics, this book will teach you. Here it is. So we just read about Jocelyn Bell, and she discovered pulsars and neutron stars. We know that. And we talked about how neutron stars are an example of extreme gravitational collapse. They're sort of in the middle. Basically, stars, when they die, they make three kinds of stellar remnants, all from gravitational collapse, because they've run out of their nuclear power and they will now collapse under gravitation into some kind of compact object. Now, this can be either white dwarfs, or it can be neutron stars, or it can be black holes, in that order of how extreme that collapse is. So the lower mass stars will make white dwarfs, like our sun, when it dies, will make a white dwarf. The sort of larger mass stars, but not the largest, will make neutron stars when they die. And the most extremely large, most extreme mass stars will make black holes when they die, because that is the most extreme kind of stellar gravitational collapse. Okay? So those are the ways. Dark matter. Okay, you want to learn about dark matter? Because we can. That's actually a pretty good topic. And I do like to talk about dark. Actually, that's a pretty good topic because dark energy we've been kind of covering for the last few lives. So we might just do dark matter now. Let's do that. Your sun will make a. The sun, yes. Our sun, the star, will make a white dwarf. Yes, indeed. Good, you revive. Oh, hi. Thank you, Emmett. Hi, N Fontaine. How are you doing? Hi, KL. How are you? What is a black hole? Sometimes it's like there's. So we just actually finished talking about the black holes. A black hole is a stellar remnant where a star, when it collapses under its own gravitation, when it's dying because it's run out of nuclear power, the most extreme type of such a collapse would lead to a black hole. Okay? It's just infinitely gravitationally dense. Um, Classically speaking, it has a point of singularity inside it where gravitation is like infinite and even light cannot escape. That's how much it's bending space and time. Okay. And it is classically described by the general theory of relativity. And we were talking about how Schwarzschild solved the equations and we got a way to describe black holes exactly. So we, even now, we actually use that, like we use, formulas or equations for the Schwarzschild radius. Um, it actually just depends on the mass of the black hole in terms of a variable, and there's some other constants, but it's actually, classically speaking, it's actually one of the more sort of simpler thing to describe. Stellar remnant, yeah, the the remnant or the object that's left over after a star dies. That's a stellar remnant. And of course, the when stars die, a stellar remnant is only part of the story. Of course, when a star dies, sometimes it also ejects a lot of its material out into the interstellar medium, so just out in space. And that can create a lot of, gas clouds, gas nebula, and such gas nebulae can actually eventually create the next star system or the next solar system like ours, and that's where we come from. So we also, everything that we're made of in this solar system all comes from a uh, the stars in the past dying and creating gas clouds. So that's the other part of the star's death, okay, that we must not forget, because that's what, thanks to that we're here. So there is also that. Infinity, that's wild. Infinite gravitational. Yes, yeah. So actually, I mean, you know how general theory of relativity is about describing gravitation using four space-time, right? So there is the three space dimensions and one time dimension, and pretty much gravitation is this bending of space-time, right? So the more gravitation something has, the more mass something has, the more it's going to bend space and time. And a black hole bends space-time so much that even light cannot escape classically. Okay, so that is why it actually is kind of easy to set the escape velocity from a black hole to just the speed of light, and then you can solve directly for the some of these equations, or some of these things that would give you the equations for black holes, like its radius, which is called the Schwarzschild radius. But of course, there are also more complicated scenarios with black holes that we're kind of not getting into right now. And also remember that I keep saying classically because in quantum mechanics we would also have some other effects that we would want to take into account. And in fact, we do take into account, and that's how we get black holes having temperatures and Hawking radiation and things like that. Okay. So, guys, I made a goal for super chats in case you want to support me. So, thank you for your likes, shares, subscribes, gifts, and super chats. I am actually going to now look for the dark matter stuff in this book. So, we have been talking about dark energy, which is, of course, different from dark matter. So, because somebody prompted about dark matter, I actually think that would be nice to talk about it because we haven't really gotten into it in a hot second here. So I'm just looking at the appendix and then going to the section here. So we've used other books. So by the way, guys, we have used a bunch of other books on this channel. Hi, Ben. Hello, I missed you. We have used a bunch of other, bunch of books on this channel to go over these topics. Right now, we are using this book, and that's the one I've pinned, which is Astrophysics for Dummies by Cynthia Phillips and Shayna Pryor. So that's just the one we're currently on. This is not the end all be all of books that we can use or anything like that, but I do try to give credit to and pin the books that we're using. And, you know, you could get it, or you could just know it that this is the book. Um, but there is a shopping option on YouTube that it lets me do, but there's no pressure. Obviously, it also just tells you what the book is. Okay. So, thank you. Aw, Jo Joa, hello, Joa Ozenho said a very nice comment. In case nobody told you this today, you are beautiful, confident, and doing a great job. Keep safe. Thank you so much. You too. Take care, everybody. 7:52 a.m. Yeah, you're like 6 hours ahead of us, Ben. My other mod is here too now. Yay. So, so I'm looking at the way that they have written this chapter. And actually, I think it will be pretty good. So, quantifying the unknown, or how galaxies work, is this chapter. From this book called Astrophysics for Dummies, and I think that will be a pretty good way to summarize. So, let's see who else is here. So N. Fontaine had requested dark matter, so that's what we're gonna talk about. What is a black hole? Sometimes it's like, okay, yeah, I responded to that already. Lots of chatter about UFOs. Hi, Mr. Dungwall. You should like and subscribe. A little late, but I'm here. Hi, Ben. Hi, Preston. Hi, the man. Hi, Shakta. So it, so light also travels through space and time, and uh, infinite gravitation will bend space time in a way where light also cannot escape. So that's to the question of light not escaping a black hole. Okay. Hi, space time entanglements. You're here. How are you doing? You look like someone who takes a person to other places one has always wanted to visit. How many mods? I have a lot of mods with the thanks to the universe. They are kindly appearing. Hi, Patrick. Okay, I'm glad both of you are moderating because that'll help a lot. Because the mods also help with answering questions and meets and greets and whatnot. So I think we will get started with the dark matter topic. I do want to. They're here. They're actually eating their snack right now. The kitty cats. I will actually get started with the dark matter topic because we haven't really discussed it from this book, and this book has been kind of nice and simple in its language. And I thought the dark energy discussions were pretty good. So why not some dark matter as well tonight? And then we can go back. I think there were a little bit more that we had to cover on dark energy as well another time. That's okay. You can fall asleep with this on, Francis. Hi, Tia. One second, guys. It's yogurt. So, the biggest thing to appreciate about dark matter is the fact that they might have and probably do have a very important role to play in how galaxies formed in the first place and even now. So, dark matter is matter that interacts gravitationally but does not interact with the electromagnetic waves. So, does not interact with light. We can't see. It's literally dark. And it is one of the five ingredients of this universe. Okay. What are the five? What are the five ingredients of this universe, guys? Quiz question. In this universe, the five ingredients are photons, that's light, ordinary matter, or baryons, neutrinos, dark matter, and dark energy. Okay, those are the five. I'll put them in the chat. It's not a place to discuss what? Okay, hopefully not about me. All right, let me type the ingredients. Okay, so those are our ingredients in this in the cosmos. And we realized that there's this other matter, which is not the ordinary matter that we know and love. And um I got you. Okay. And what we're made of, there's some other matter which is also contributing to gravitation and to gravitational effects that we can feel, that we can observe, but we can't see this type of matter. So let us look at this from this book. So matter is, so some of you mentioned some types of matter when I was asking about um, the cosmic ingredients. So a lot of the matter that you're mentioning, neutrons, baryons, carbon, these are actually these are actually all ordinary matter. Okay? So matter is by definition the material that makes up the universe. The earth is made of matter. In fact, a lot of matter that is consisting of oxygen, iron, aluminum, and other elements, as are planets, stars, and everything else out there. Galactic source material is matter, but matter of a particular sort. Gas and dust, sure, but also stars, dark matter, and even black holes make up the composition of a typical galaxy. So, dark matter is something that is part of even our own galaxy. Okay? I like listening to your streams and the way you explain things. Thank you. Thank you, Steve Johnson. Thank you for being here. And please do like and subscribe. So, this topic that we're talking about right now, although a bit mysterious sounding and is still a mystery, is still something that we actively do research on to figure out what is this dark matter, what is the type of particle, or what it's really made of. But it is something that affects us even in our own galaxy. It is not sort of like this distant, far away thing necessarily. So, for example, when we talk about dark energy, which is a separate topic, one of the ingredients of the universe as well, but we talked about it in the past couple of lives. When we talk about that, can you still hear me? I just saw the live kind of become a little different. Okay. So, when we talk about dark energy, we know that that is something that we observe for large scales only. So, universe as a whole, at larger distances, dark energy comes to play a role. But dark matter is something that is quite a bit more local. It is something that affects us even now, okay, or even in this galaxy. So did we lose connection? Oh gosh, I hate when that happens. So you can see me now? Hi NPC, hi Steve. Thank you. So, so keep in mind that dark matter is an astronomy, cosmology, astrophysics topic, whereas dark energy is a cosmology topic. Cosmology deals with the entire universe. Cosmology deals with large scale structure, large distances, okay? So it's not necessarily something to do with just our galaxy or the local cluster or something a bit more local. Dark matter is. Dark matter is a topic from all of those fields. So it is something that um if you want to study, you can study it in astronomy, in astrophysics and cosmology because it also is a topic in cosmology. So even our own galaxy, I want you to appreciate this, has dark matter. Okay? So Hubble made a discovery that this book talks about in chapter 9. All galaxies seem to be moving away from us, and the farther away they were, the faster they were moving. That idea led to the discovery of the expansion of the universe. So this is something to deal with dark energy. So don't get it confused with dark matter. We talk about this more in chapter 13, but the key point here is that astronomers' ideas about how the universe formed and what's happened from there require more mass and energy than can be seen in the observational universe. And that's where dark matter comes into play. So, the nice or, well, interesting thing is that dark matter, it's something that we see the effects of in our own galaxy, even, so which is quite local. And it also plays a role in the formation of structure in the universe. So, the thing I was saying about large scale structure, well, the first galaxies forming, the first little push that gravitation got in spots of this universe to then form the first galaxies and stars, which then led to all of us being here. We think dark matter has a role in that because there wouldn't have been enough mass to really give gravitation that extra hand in order to make the first galaxies and stars. So there has to be some other matter that we think is also the case, and that is consistent with all these other phenomena that we see even in our own local galaxy, which also indicates extra matter. So do you see what I'm saying? Like dark matter, the the evidence of it and the role of it is sort of multifaceted. There's a role of it in our galaxy, and there's a role of it even in the universe and in forming galaxies in the first place. So, how matter, for example, is distributed in the universe, how the galaxy is formed, and how, there is some geometry, some distribution of matter in this universe. We think that dark matter actually has a role to play with that. And so, hi, Nicole. Oh my goodness. Hi, Nicole. My superstar moderator is here who helps me to meet all my goals. Hello, sunshine. I hope you're having a great day. Thank you, Nicole. Aw. Thank you, thank you, thank you. Everybody, I will read your comments in just a moment. So, once again, what has happened in this universe since it started seems to require, as in, there used to not be any galaxies, obviously, and now there are galaxies. For example, that is one of the evolutions of the universe. We've It seems to be the case that there wasn't enough matter for that to really take place. We needed some extra matter, and that is consistent with us also finding dark matter. in various different ways. Dark matter is thought to make up about 27% of the universe. The dark part means that this kind of matter cannot be detected with any of the usual techniques, but it does exert a gravitational force on other matter. So, as I was saying, this basically interacts gravitationally. It affects things gravitationally. It affects how fast or slow stars and other objects move, for example, which is a gravitational effect. But it does not interact with ENM, with electricity and magnetism, or with light. So we can't see it. So dark matter does not give off any electromagnetic radiation either. So remember how, I mean, in this universe, like usually when we look up at the night sky, like what do we see? That is basically ENM, right? Like the light from different objects reaching our eyeballs. um Basically, if it's visible light, then it can be processed with our eyes, and if it's other type of light like radio waves or gamma rays, then we have other types of detectors for that. Our eyes can't handle that, right? So basically, all of that all of that is a type of light, or a, basically objects having a luminosity that it's emitting, some light that it's emitting, and we are able to see it or measure it or detect it. And that is a that is a way for us to know that the thing exists. Well, for dark matter, if it is not emitting any light of any wavelength, then it's going to be very difficult to see it. Okay, so and remember, we've kind of talked about this in the past, like as to what candidates of dark matter there could be. And you could imagine some like darker objects, like for example, even our moon actually doesn't make its own light, right? It is reflecting the sun's light, or the earth, right? I mean, there is some anthropogenic sources of light here, but it doesn't make its own light for the most part. So from a big distance away, if there were, I mean, one could imagine that if there were a bunch of these objects that are kind of like massive, but you can't really easily see them, maybe they contribute towards dark matter. In fact, people thought that there were these compact objects in the halo of our galaxy that could maybe be sort of very dark, as in they don't have much luminosity that they're emitting at all, but maybe obviously they have some mass, and that could be the dark matter candidate. But actually that was kind of ruled out because we didn't, there were there are actually other ways, um gravitational lensing, there's other ways in which one can sort of see things. Like basically, if it is a compact object like that in the halo, then we would expect it to do certain other things which it didn't do. So, you know long story short, we thought about ways in which to account for dark matter, and it kind of didn't really pan out. So we still don't know exactly what it is, but we know it's there. It is something that does not interact with light. It does not give off light. Now, could it be something like a compact object? No, it can't be, So there have been some iterations of like people thinking about some candidate of, oh, could it be that? But it's not, right? So that's kind of where things are. And but once we accept, though, that dark matter is something, then there are other questions, for example, of like not just the nature of it, like what particle or whatever the frick it is, but also what kind of role it may have played in the universe as a whole. Okay, so that's some of the things that we're talking about. So from doing the various sort of calculations and the various different methods, some of them astronomy, some of them cosmology, we have found that it makes up about 27% of the universe. So the cosmic ingredient list I was telling you, the five things, dark matter is a substantial fraction of that. So ordinary matter is only like 5% of the energy density of this universe, whereas dark matter is like 27%. So it's quite a bit. It's a lot more than ordinary matter. So the dark part means that this kind of matter cannot be detected with any of the usual techniques, but it does exert a gravitational force on other matter. Dark matter doesn't give off any electromagnetic radiation either, so it cannot be seen directly with an X ray telescope or any other kind of telescope or even our eyes, right? I mean, if your eyes can see dark matter, please do let us know. If you think dark matter is weird, wait until you hear about dark energy, which we did talk about for the last couple lives. So we kind of already launched into that on the channel here. For now, let's focus on the normal matter that makes up galaxies, also known as detectable matter. What is known about galaxy formation? The prevailing theory is that galaxies have formed and matured over time, likely starting as elliptical galaxies, but perhaps colliding and merging into completely different shapes. So I'm not so sure about that, as in like the elliptical thing, right? We know that there are basically different shapes of galaxies: elliptical, spiral, and irregular. So, you know, maybe they started off as, I actually don't know. As you look for galaxies at higher redshifts, so that's like farther away, you're looking back in time at galaxies that formed a long time ago, when the universe was younger. These ancient galaxies look very different from today's majestic spirals and ellipticals. Ancient galaxies are comparatively lumpy, for lack of a better word, with knots of bright material where stars are forming at a rapid pace. So, the first galaxies and first stars then led to the next generation of stars and galaxies and things like that. So, the Trinity: gravity dominance, instability, and collapse. If you think the main forces at play in your life are love and physical attraction, weird, you're half right. Without gravity, the attractive force that pulls all objects in towards its center, you'd be floating away from the surface of the Earth, and the Earth would not be pulled into orbit around the Sun. But that's another problem entirely. Gravity plays a central role in your everyday life, and that the same is true for galaxies. So, if not for gravitation, we would not have galaxies for sure. We would not, basically, in the smooth universe, if we did not have some inhomogeneities and fluctuations away from being smooth and clumping of matter, then the first galaxies would not be forming. Did I lose connection again? Oh, I didn't? Oh, thank you. Okay, great. So, of the major forces at play within a galaxy, gravitational dominance and instability top the list. We cover gravitational instability in chapter 11. The formation of stars, the universe, and everything in between all begin at the beginning, cosmically speaking. Everything comes back to primordial dust and gas. So there's a bunch of dust and gas. A drop of water mid-air. Okay. When it comes to creating galaxies, though, you can add another level of detail. Clumps of gas and dust begin to hold together in piles of dark matter until the density increases enough to collapse. This concept is similar to the way stars form, but on a much larger scale. So the first galaxies, right? One of the main ideas about how galaxies form explains that when a cloud of gas and dust gets large enough, gravity may overcome gas pressure, causing the cloud to collapse. Hi, John. If there is any asymmetry, and there is always asymmetry, the system will start to rotate. If the collapse is rapid, stars may form with chaotic orbits, resulting in an elliptical galaxy. If the collapse is slower, so now we're talking about a galaxy length of collapse, a disk galaxy will have a chance to form, which is, guess what our galaxy is? This idea is called the theory of gravitational collapse for galaxy formation. So this is basically kind of describing how a galaxy forms. Okay? The gas that's caught up in this formation process gets heated due to shock waves and then must cool according to the law of radiative physics. The cooling rate depends on the temperature and pressure of the gas, but it happened fairly efficiently in the hot, dense early universe when many galaxies were first forming. So you will kind of see this type of thing happening, like very similar language even for stars. When stars form, some of this like gas and dust and cloud of gas, blah, 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 you know, getting close enough, then hot enough, and then cool enough. All of that is actually involved in star formation as well. But this is basically galaxy formation, which is, of course, more bigger scale. Okay. So that's what's happening, or that's what happened. Thank you, NPC. Thank you, Jacob. Thank you, El Hode. And if we don't know how to perceive dark matter, then so there are evidences of dark matter. So one of the biggest evidence that people look at, for example, is the velocity curves of um, stars in the galaxy. And we actually have talked about that in a lot of detail in the past. So basically, the uh, rotation, basically the center of our galaxy, for example, has a supermassive black hole and then a lot of mass in the center. And things are kind of going around it. Even we are actually going around the center of our own galaxy. We have only made like 20 trips around the center of our own galaxy. So in that sense, we're like a 20-year-old in our galaxy, okay? So the speed at which stars, say, are going around the center, this can be observed. And we expect that behavior to be a certain way, and we saw that the behavior is quite different from what's expected if normal matter was the only thing that's in the galaxy, and that is one of the direct evidences of dark matter in our own galaxy. And there's other things too. So there is a number of like multiple ways in which we know that there is a problem with us accounting for all the matter with ordinary matter. Okay, so um I think some of the stuff here will actually help with this question as well, because we're gonna get into the this slow and fast thing that I was just talking about. So aliens, well, when you ask about aliens really quickly, I would say the best way to search for aliens is to search for exoplanets, and that is something that is already happening. You could go and look for exoplanets because for aliens to exist, we need worlds that can support them, right? So we can study exoplanets. There is one supermassive black hole at the center, as far as we know, but there are more black holes in general. The supermassive one, we expect that there is just the one, yeah, at the center. We would want some kind of life to be supported, right? I mean, if not a planet, what else would it be? Can't be stars. Those are too dangerous for life. Can we get 50 likes? Ahmed, did I lose this connection again? Okay. Do you ever feel the Earth's rotation? Probably not, right? Uh, neither do we. So the Earth rotates about once every 24 hours, and a person at the equator travels at what seems like an alarming pace of 1,000 miles per hour because of that. However, you're rotating right along with the Earth. So you don't notice the Earth's rotation. I mean, if you do, please let us know. Similarly, all galaxies rotate, and our Milky Way galaxy is no exception. So I was talking about our solar system rotating around the center of our own galaxy, but guess what? Even the galaxy itself is rotating. So it spins at about 130 miles per second, but because you're inside the galaxy, you don't feel the effects of its motion. So now, why do galaxies experience rotation? Look to angular momentum. So angular momentum is a type of thing that hopefully you do know about. Angular momentum adds in the idea that an object's position and the direction of its motion changes over time as compared to a fixed reference point. If you slide a block down a slope, it has linear momentum. If you attach that block to a string and swing it around your head, it also has angular momentum. Additionally, scientists use gravitational torque to model exactly how fast galaxies are rotating and how infalling gas gets incorporated. The term torque, which is kind of the counterpart of force in rotational stuff. So in physics, torque refers to the force required to rotate an object around its axis. Torque is described by the equation Rf sine theta, where r is the radius, f is the force, and then sine theta, where r is distance from the center of mass to where the force is applied, f is the applied force, and theta is the angle between the force and the lever arm. Hopefully, these are things you have covered in your classes in school. So now, add gravity as that force into the mix, and you will get gravitational torque. And you can understand gravitational torque as the force of gravity bearing on a mass's center of gravity, causing it to rotate around some fixed point. So this is sort of a pretty Newtonian way of kind of describing how these things have what do you call it? A rotation. Because so far what we have described is sort of Newtonian mechanics. Okay, so scientists apply the concept of gravitational torque to help understand how gas particles can lose their spin and join in the rotation of a galactic disk. What does all this physics have to do with galaxy formation? As galaxies form, the collapsing core is subject to forces from nearby clumps of matter. There is matter and there is clumps of it. This force, plus the original motions of the gas and dust that collapse down, results in a spinning disk of material due to conservation of angular momentum. So, conservation of angular momentum is a big part of everything. I mean, even in our own, uh, why do we rotate, right? Um, the Earth, Mars. Uh, we're all spinning, right? Actually, I think Venus does not rotate very much. It rotates very slowly, if I'm not mistaken. But why do we have angular momentum? It is actually to preserve the angular momentum of the gas nebula that we come from. Okay. So in our case, we are the solar system. We come from a gas nebula that condensated at some point. I'm spinning. Yes, we're all getting dizzy from all the spinning. So we actually come from some gas nebula that condensated and went through the process of becoming our solar system, which is the sun and the planets and the moons and all of it, right? Asteroids, whatever. Well, when we formed, as in when our solar system formed, most of the mass of the gas nebula went to the sun, and most of the angular momentum went to us, okay, as in the planets. So we are spinning. We're all spinning. We're dizzy. I mean, we're not because we're spinning along with everything, so we don't notice it. But for us too, conservation of angular momentum is the reason why we have spinning planets, okay? And we don't have much of a spinning sun because pretty much the total angular momentum had to be conserved before and after this solar system formation. And so we got a bunch of the angular momentum, almost all of it, and most of the mass went to the sun. And which is why it is the sun, right? Because you have to have a substantial mass for that hot, cold thing to happen again, which is like basically tug of war between gravitation and thermodynamics to make a star, right? So yeah. So if you think those star clusters are complicated, now think about a galaxy with billions of stars. So, a galaxy formation or a star formation can sound pretty complicated, but then think about the entire universe and its distribution of matter, which is basically its formation of galaxies and how that happened. So, it is good that we just now talked about a galaxy formation because the context will help. So, here in the world of astrophysics, we try to blow your mind at least once a day. So, consider this your daily dose. Our sun and our whole solar system orbit the center of our Milky Way galaxy. We knew that. I told you that already, so that's not too mind blowing. You can use the orbital velocity of the sun, which is about 200 kilometers per second, to find that the solar system's orbital period is about 225 million years. That's how long it takes us to take a single trip around the center of the galaxy, which is how we know that when the dinosaurs were on Earth, they were on the other side of the galaxy. Remember, we talked about this because, well, our galaxy is very old. It's basically 13 billion years old, and this 225 million years number, we take that and we find that when the dinosaurs were here, guys, we were on the other side of the galaxy because we are also rotating around the center of the galaxy. Okay. To put that into perspective, over the whole time that the Earth has existed, um, 225 million years, yeah. The solar system's orbital period around the center of our own galaxy is 225 million years. And I believe the dinosaurs are like older than that, right? So, a single trip for us to make around the center of the galaxy is 225 million years. Okay? So, to put that into perspective, over the whole time that the Earth has existed, it's only orbited the center of the galaxy about 20 times. I already told you this. Our age, our galactic age, if you will, is just barely over a teenager. So our sun and us, our galactic maturity is just about 20 years old, if you will. 20 of these galactic years. So think of Kepler's third law. So these are just classical mechanics, Newtonian mechanics that we're considering right now, when you have one object orbiting another. If you assume if you assume that most of the mass of the galaxy is concentrated at the center, or at least inside the orbit of the sun, basic calculations estimate. Oh, so by the way, you're gonna see the thing I was saying about the velocities or the rotational curves of the stars. So guess what? Guess what? Guess what? We can learn something from Kepler's third law. We know that there is a supermassive, I mean, that's why we're orbiting the center of our galaxy. Obviously, there's a lot of mass that's concentrated in the center. So, if you assume that most of the mass of the galaxy is concentrated at the center, or at least inside the orbit of the sun, so like where the sun is orbiting our galaxy, basic calculations estimate the mass of the galaxy at about 100 billion solar masses. So hold on, the sun orbits the center. Yeah, yes, of course it does. Yes, did you not know that? Of course the sun orbits. The moon orbits us. Stars are not stationary, no. Mm-mm. The moon orbits us. We orbit the sun, and the sun along with all of us. Because wherever the sun goes, we go. The sun. So the moon orbits us, we orbit the sun, and the sun, along with all of us, orbits the center of our galaxy. And a full trip takes 225 million years. Okay. Hi, Carniferous. I'm in physics grad school right now. What are you talking about? I taught the UOs in, what do you study? Um, we were talking about astrophysics. Hi, Junkyard. I love it when smart and pretty women endlessly monologue about interesting things. Well, we were on the other side of the galaxy. So what I mean by that is dinosaurs are really old. I mean, if someone took a picture of Earth or the dinosaurs, then yeah, we could have seen that we were on the other side of the galaxy. I like that when a hypothetical observer, they do not see the Earth of 2026, but rather that of 1926. Oh, so they would see Einstein. Mm, I like that. They would see Einstein's Earth, not my Earth. Poor things. Nothing's ever perfect. Nothing is a perfect circle, usually. So, so let's think about Kepler's law real quick to finish this up, okay? If you assume that most of the mass of the galaxy is concentrated at the center, because why? Is that a fair assumption, guys, by the way? Because we can question every step of this, uh, you know, logic or calculation. Because most of the luminosity of this galaxy that we're part of, Milky Way galaxy, is within that distance. So from the center of the galaxy where we are, like let's say this is the solar system, this distance, pretty much most of the luminosity of this galaxy comes is contained within that distance. Now, I told you earlier that when we look up at the night sky, we see objects that, emit light, that are basically sources of light, and the visible uh ones, as in the visible light that enters our eyeballs and can be processed with our eyes, we see that, right? And that's how we know that things are there. Generally, we don't know if something is there if we can't see it with some kind of instrument, observation, something, right? Because, I mean, it could be light that is a different wavelength and we can't see with our eyes, but we can pick it up with a different type of detector. So what do we mean? By that, we generally mean that we're picking up on a brightness level, right? Like a luminosity, a power. Because there's energy, but then energy divided by time is power. Okay? So like joules per second is watts, right? So like basically this is saying, oh yeah, that thing is emitting energy. Like let me see how much, and let me observe that, let me measure that. And not in New York City. Are you in New York? Not able to see any stars? So I feel that maybe you should go up to Rhode Island or something. So yeah. So luminosity is an important term that you'll come across in astronomy. People are measuring this all the time. So when I say that we assumed that most of the mass of this galaxy will be contained within the orbit of the sun, well, because most of the luminosity was contained in that. And um, what do you call? Like, for example, the halo of our galaxy looked pretty dark, looked like pretty empty in the sense of luminosity. Okay? So, all right. So this assumption was quite reasonable for quite some time, because this assumption, as in thinking that most of the mass is going to be concentrated at the center of the galaxy and pretty much well contained, like well within the sun's orbit, was a good assumption, because most of the visible material in the Milky Way seems to drop off dramatically after you get out to the edges. So this is what I mean. Like most of the luminosity, whether that's visible, radio, gamma ray, whatever wavelength of light, was well within the sun's orbit. Okay? Yeah. Okay. So Kepler's third law also shows that. So by the way, remember what Kepler's third law, Ben? Can you put in the chat what Kepler's third law is for the vast majority? Yeah. So, Ben, can you put Kepler's third law in the chat? Because remember what Kepler's third law tells us. It has to do with the period. Remember Kepler's laws for planetary motion? We understand about the orbits of our planets around the sun and all that. Of course, it works on what do you call it? It works for this type of orbiting as well, because pretty much it's just about masses. But this is super relaxing. Just found this. Thank you, Junkyard. You should subscribe. I hope you did. So remember about Kepler's third law. It tells us about the orbit. And we found that it's elliptical orbits actually for the planets. We found about the how to measure the period of the orbit. Kepler's third law of planetary motion states that the square of a planet's orbital period is directly proportional to the cube of its average distance from the sun. So, in relation to the planets and the sun, that is the third law of Kepler. So, you're basically getting a measure for the orbital period. Okay. So, we're able to get something. So, in the case of our galaxy, so, once again, Kepler's third law also shows that objects orbiting a massive central object at a large distance will move more slowly than those closer to the mass. And why is that? Because the orbital period is directly proportional to the cube of its average distance from the sun. So, the farther away you are, that period will be longer, which means the velocity is shorter because period is a time. So, so in the case of our galaxy, uh, so once again, this period being longer versus shorter, okay? Because look at what Ben put. From that period, you can figure out how fast something should be moving. Okay, so orbiting a massive central object at a large distance will move more slowly than closer to the mass, and that comes from Kepler's third law. All right. Thank you, Hazel girl. Hi, Wisdom. Did Kepler use your mama? Hi, comrade. Hi, Gunnar. Hello. Good morning from Europe. Hello to Europe. So, orbital period based on average distance, meaning velocity of that revolution will be dependent on that. So, the farther away things should be moving slower. In the case of our galaxy, so, and mind you, we are talking about. Thank you so much for liking and subscribing. So, we are talking about our own galaxy, not a faraway galaxy, not something so exotic that we cannot reach it. I mean, it is hard to reach, even within our own galaxy, but this is our very own galaxy. Okay. So, this is where I think this is so powerful because this situation that we're talking about affects even our own galaxy. In the case of our galaxy, if most of the mass is concentrated in the visible portions of the galaxy, so where the luminosity is mostly contained, objects that are seen to be farther out from the sun, so where the sun is in orbit around the center of the galaxy, farther away than that, like think about the halo of the galaxy, farther away, such as globular clusters, those things should be moving more slowly than the sun around the center of the galaxy. In fact, however, those globular clusters have orbital velocities that are even faster than the sun. So, what they saw is that these farther away things that are farther away from the galactic center than our sun, were actually traveling faster. They were not slowing down, they weren't even really constant, but they were getting faster as you got farther away. Yeah. Yes. I just like listening to someone. Well, we're talking about our own galaxy and dark matter. We'll get into it. Interesting listening about our solar system. Yes. Hi Dan. Hi Mr. Fundles. Hi Hazel. Hi JF. So, where our sun is around the galactic center. Within that distance from the galactic center, we see most of the luminosity, from which we can fairly assume that most of the mass is also contained within that radius. And if that is the case, according to Kepler's laws, the things that are farther away from the galactic center than our sun should be getting slower and slower in their rotational speed. But that is not the case. We actually see that they're getting faster. Lo and behold, that is quite a shocking result. Okay. So, this is one of the evidences of dark matter. All right. So, what you have your hands on, folks, is a conundrum. Objects move according to Kepler's third law. If they're going too slow, they fall into the center of the system. If they're going too fast, they escape from the system completely. So, that's the other thing. Why didn't they just escape? If these outer globular clusters are moving faster than expected, but are also bound to the system and are not escaping, there must be significantly more gravity and therefore more mass in the galaxy than can be seen. Sorry, I spat on you in my passion. So, thank you so much for liking. Oh, thank you so much for the gift. Sorry, I sprayed it instead of saying it. Um, but how exciting is this? You can spit all you want. Aw, you're so kind. Thank you for the gift. So, these frickin' globular frickin' clusters, if they're moving so fast and they're not escaping, what the frick, right? If these things are moving so frickin' fast, why didn't they just escape this galaxy? Mother frickers, right? Why didn't they just escape our galaxy, our galactic center? What that means, unfortunately, ladies and gents, is that there is more gravity and there's more mass in our galaxy than we can see. And by see, I mean that we can detect in various wavelengths, etc., etc. No, the universe expansion, that is about dark energy. That's another whole topic, guys. No, 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 no. This is about dark matter. We're talking about our own galaxy. This is quite local. Okay? So the dark energy thing that you're talking about, that is very good. That's great. And we talked about it um in the previous lives. That's dark energy. Now we're talking about dark matter. Matter. Okay? So, calculations show that you need about 20 times more mass, 2,000 billion solar masses in our galaxy. So, we need about 2,000 billion solar masses in our galaxy, or at least inside the orbit of the globular clusters. So, these globular clusters that are moving faster than they should basically mean that we need 2,000 billion solar masses more in our galaxy. Because the material cannot be sensed with any of our normal ways of studying electromagnetic radiation, that means it must be, you guessed it, dark matter. Okay? So, with that, I hope I've convinced you that dark matter is a topic of great interest and mystery that affects not just cosmology, because it does affect cosmology, it affects what we think, um, is the process behind galaxy formation in the first place. But it is very much local to us. It is very much in our lives in the sense of our in our own galaxy. So it's a topic that can be studied in astronomy, astrophysics, cosmology, all of the above. Whereas as opposed to dark energy, which is more of a cosmology topic and affects expansion in the universe at large scales. So, yes, Ahmed, that's a lot. Hi, Zoe. Okay, we will stop there tonight and continue next time. Thank you, Zoe. Thank you, NPC. Thank you, Hazel. So, next time we will talk about galactic structure. Actually, we might not talk about galactic structure because I kind of want to talk about um because galactic structure we've talked about. I mean, it's been a while since we talked about it, but it's not really about dark matter. I kind of want to talk more about dark matter next time. So let me go to that chapter and look at it. So this is great that we started off. I think you can speak Hindi. I can. Hello, Chandra Pan. How are you doing? Thank you for subscribing. Please do like and subscribe. Canadian, I am in the US. That's what they're doing. Dark matter is the problem. I have to use the. Please do use the bathroom. Hi, Matt. Hi, knee crappers. Hi, BLVD. Hi, coach. This is the book that we have been using, and it's also pinned to the live, I hope. Astrophysics for Dummies by Cynthia Phillips. And Shayna Priver. Hopefully you enjoyed that, guys. And hi, Omega. Thank you for liking the live and for the gifts and super chats. Hi, Milo. Thank you, thank you, thank you. Okay, so next time we will, what is the time? 1:58. We will, let me just find, oh, yes. So I am really glad that we started with that note on dark matter because, people do wonder exactly how we know about dark matter in our own galaxy. And this thing that we just touched upon, this doesn't have much math actually. Hi Israel, hi El Huday, hi Space Time, hi Manhaj, hi Ben. Hi, El Hodedor. Oh, by the way, I'm going to do the top fans in just a second. So, this book is actually extremely readable. It's not a very difficult or dense book at all. It's like literally for, helping people to understand these concepts and whatnot. So, um, it's very like simple. It's not bad. Okay. So, I'm glad we talked about that particular conundrum with dark matter and us finding out about the stars moving faster than they should, farther away from the galactic center. That is actually a very, prominent and well known and one of the first sort of big evidences of dark matter, and something that really blows people's minds and, really goes against what we knew and understood and shows people like what we're dealing with here. So I'm glad we talked about that. And then moving on from there, we will. We will go to chapter 15 next time. Maybe we'll discuss a little bit about general relativity. Maybe, because we've done that as well. or we might just get into galactic glue, which is dark matter. So something that dark matter is kind of known for is being this galactic glue that, keeps galaxies together and also might have helped them form in the first place is very interesting. Hi, Sunny or Sunny. Hello. Cosmic sleep. We need more similar robots looking like you. Oh, well, thank you. I don't know if that's a good thing or a bad thing if the robots look like me, but sure. So, galactic glue, if the puzzle we've laid out so far is still missing a few pieces, dark matter will fill in at least one of the gaps. So, dark matter as a galactic glue, we will talk about next time. This author is kind of funny. All right, I bookmarked the page that we will start from. And I am so glad whoever asked about dark matter tonight because I was ready to move on from what we were from dark energy and touching upon dark matter because I mean I love talking about dark energy too, but we hadn't really talked about dark matter in a hot minute. So I am glad for your questions, guys. I really appreciated it. Everybody that you know chimed in and asked questions, thank you so much. I will look once over at all the comments again, so I'm still sticking around for a bit, but thank you so much, everybody. Thank you, Elhude. Thank you for the likes and the shares and the subscribes and the gifts and super chats. Okay, keep them coming. I will have more videos, clips, shorts, and everything posted. I'll go live again. I hope to see you there. And if you do the notifications and subscribe, then hopefully I see you again and again on these lives. Okay, because that's where it becomes more interesting and you can kind of follow along these topics much better. Okay. Thank you, everybody, for stopping in. Let me get up and actually warm my tea here, and I will title the live. I haven't done that yet. What should I call this live, Ben? Thank you. Good night. You need some sun? Yeah. It's been rainy here. Let me throw this out and get my tea going. Acacio, Scott. Who else? There are several people that I really missed on this live. I hope that you see this and hear me and comment. Where were you guys? Mm-hmm. For questions, what do you mean? It's always wonderful, Baji. By the way, do you use Grok or Gemini or Copilot for questions? What questions? I think Gemini uses me for questions. So somebody has to teach Gemini, you know? AI won't learn on its own. We have to teach it. Astrophysics. I actually work on teaching AI. I don't think Gemini is one of the ones that I've taught, but um I actually work on making AI models better. So I can assure you that AI needs to be taught a lot before it can be helpful, although now it is starting to be. And without people, human beings, teaching AI, I don't think you would get the utility out of AI that people are hoping for. Mercury is my ruler, so I have a lot of intelligence to gather from you. Mercury is my ruler. Thank you. Name class, dark matter. Adam! Hello, Adam. How are you doing? Do you search in the 11K? What does that mean? Hi, stay tuned. Thank you. You're God's given beautiful. Thank you so much. When working with a, do I search in the 11K? I don't know what that means. Thank you, stay tuned. Hi, Adam. Very good. That's okay. How are you doing? This outfit, I mean, it's just a dress. My birthday's in October. October 17th. I don't know. I'm a Libra. Hmm. Do I have a husband? No. So funny you say that I work as an AI trainer. Oh, that's cool. See, Adam is doing it too. Here's my dress. It's just a little dress and a sweater. Libra is another brainiac zodiac. What's your zodiac? What's yours? Adam? So, Adam, are you in the summer now? I forget, which year are you again, Adam? Are you in summer semester? Are you going to be pretty free? You should resume your moderation activities and duties. Thank you, Adam. El Hodedor is saying Pisces, Sagittarius. More than 70% of my friends are Libra. Oh my God. I don't know a lot of Libras, except for my brother, of course. We're both Libras. Um, Hello, Liqueur Butte. Thank you for the $2. Will you share with us the secret of anti-gravity? Yes, and I did. I did last couple lives. We talked about dark energy there. So that's anti-gravity for you. Thank you for asking. You have dreamy bedroom eyes. Dark energy inspired me to tell you that. Thank you, space time. Scorpion constellations, Libra is. I do like being cozy. I'm free for the summer now. So my capstone. Thank you, Adam. It's so good to have you back. How old will you be in October? Well, I'll be more than 21, that's for sure. Hmm. Ahmed is saying, I'm a Gemini. Libra is all smart and cozy. Cool. Libras are. So you're a Gemini. Because happy almost birthday season, Gemini. Gemini season is coming up, right? The babies have gone upstairs. Hi, Shivi. Hi, Abu. Sorry to hear that. Thank you for liking the live, guys. Oh, June 18. Hi, Bende. What are you talking about? You have wife and kids? Your beauty is electrifying. Thank you, Benny. You should say that in a super chat. Shout out to Candice. Who's that? The baby Bengalis, yes. Mm-hmm. All right, Ben, are you ready? I'm about to name the live. It's surprisingly civil in here compared to last time. Ethiopian. I really do like Ethiopian food a lot. In fact, near me, there's Ethiopian restaurants and I eat there. Electric Girl. You're more than welcome. Thank you, Benny. I used to work with a guy called Benny. He was really nice. Now I miss him. So I'm naming the live. Did he have jets? Ah, they're really nice people. Why do you miss Benny? Because I don't see him anymore. Because I don't work there anymore. Hopefully he's well. Benny, if you're seeing this, I miss you. Mwah. Mm, mm. So please do rewind the live. We are actually finishing up. We started a while ago. I bet Benny misses you too. Oh. We did talk about astrophysics. We've been talking about astrophysics the whole time. So you should definitely rewind, okay? Thank you, Liqueur. When are you getting a boyfriend? You're too beautiful to be single. Well, I'm not sure if it's any service to me if I'm the beautiful one. You know what I mean? Like, what does that do for me? If I'm too beautiful to be single, if I get a boyfriend, like, what does that do for me? I'm in a conundrum. A bigger conundrum than the black hole, or sorry, the dark matter one that we just discussed. Hello, Shaurya. Hi, Javaris. Hi, Nagato. Hello, Nick. What is my key to happiness? This. Physics, astrophysics, astronomy, cosmology, kitty cats, travel, nature, ocean, luxury. You're beautiful, but happiness and contentment is more important. Exactly. I do believe that. Women like you don't stay single for too long. Do you believe in karma? I do. Hi, Tony. Hi, Milo. Oh my gosh. You guys are funny. That's the name of their boyfriends. Travel cats. Travel, luxury, kitty cats, nature, ocean, the continents. I really need to go to South America. Your personality is so heartwarming. Thank you, Milo. Jeremy. Jeremy makes me happy. Oh. I mean, yeah, whenever I go live and Jeremy pops up, I'm like, wow, Jeremy. Actually, let's see, Jeremy, where you rank in the top fans. Number one top fan is not you, Jeremy, my love, but it is Liqueur, the Butte. Number two is Ahmed Cunningham. Number three is Ben, my friend. Number four is El Huday Darrala. El Huday, how are you? Number five is Mr. Drew, my goodness. Number six is Keith. Number seven is Space Time Entanglements. All of the entanglements. Number eight is Mikey. Number nine is Jeremy. Oh my God, Jeremy, you should do something about that instead of just speaking about it. You should do a super chat to bring yourself up from the number nine slot. Number 10 is Comrade Jones. You thought you were number one, you're not. You have to do something about that. You're number two right now. What about Taco? Um, oh, thank you for the floating heart, Jeremy. But I think you gotta do more than that because okay, number seven. Now you're number seven, Jeremy. Taco Delight is number 14. Hi, Milo. Milo Torres has sent a gold coin. Wow. Thank you, Taco. Thank you, Taco Delight, for the gift. Thank you, Jeremy, for the gift. Love you, mean it. Oh, thank you, Taco. Love you too. Mwah. Thank you, thank you, thank you. Hi, Milo. Thank you for the gift. Mwah. Mwah. Thank you, thank you, thank you. I know we need a lot of money for just the gas bill. The gas bill last month was $160. I hope it's going down now because it's spring, but you know what I'm dealing with here? Wow, what a cool ring. Thank you. I got this on an island. These the earrings too. Gas is so darn high. What's happening, nerds? Hello, Mr. Vision. Hi, how are you doing today? Hello, Joseph. Um, thank you. They're heart-shaped earrings that I also got from the same island. I don't know why, but you look very similar to Speed. I don't know who that is, but okay. Why are you pretty? Hello, Ramo. Hello, Taco Delight. Um, what's my favorite food? My favorite food is the Indian cuisine, where I come from, and followed by Italian. I love a good bolognese or, like pasta with wine. Um, but I also just really like homemade, home cooked Indian food, like made by family or close friends. Kind of depends on the circumstances, like the situation. Like eating out, probably my favorite is Italian. In fact, I want to go to Italy just for the food sometimes. Speed is a football player. And that I look like a football player? Okay. Can we get 80 likes? You finally got below 100 degrees? Where are you from? Hi, Giorgio. Hi from Italy, darling. Where are you from? I was just talking about Italian food, and now I have an Italian in the chat. Hello, Giorgio. Where in Italy are you from? Roma? Milan? Where are you from? What a different taste of cultures. Really, are we still going through the dummies? Can I cook? No. Who does your eyebrows? Who does your eyebrows? Like, I do my eyebrows. Yes, we have 80 likes. She is Vulcan. Can you clean? Yes, I can clean, but I mean, you have a housekeeper, right? Why are you asking me if I can clean? I can clean, but nobody cleans better than my housekeeper. She's very good. In fact, I'm gonna make a video about her cleaning. Has anyone called you a Latina? You're stunning. Oh, thank you. Yes, people call me a Latina all the time. In fact, in my neighborhood, people only speak to me in Spanish. and I should know some more Spanish. Can you come to America so we can love you? I am in America. You should come to Italy. Do you ever been to Europe? I'm close to Milan. Are you able to cook? I am not a big cook, Giorgio, so I would be depending on your cooking. And yes, I have been to Europe. I've been to Rome, actually. I've been to Italy, but not Milan. I was thinking about going to Milan, but I have been to only Roma in Italy. And I learned to say grazie. Yes. And of course, I love the food there and the Colosseum and the Pantheon and the food and the tours. My tour guide was really nice. I saw that the big fountain. Do any of these things mean anything to you from Italy? And I love Europe. I downloaded your pic. My pic? From where? Are you near an Indian community where you bunkers with the festivals? B is my favorite mamacita. um, I do have Indian friends, but I don't know if I have a big community yet here in Boston. Why are Indian guys so argumentative? I don't know. I'm not an Indian guy. Actually, but you know, you're right. You're right about that. I could cook for you, maybe not in Milan, but New York. Good. I need you to cook in all the countries because I like traveling. If you want a suggestion, Milan is only good for shopping. You should go to Florence, is way better and historical. I subscribe your channel. Thank you. Next time I'll teach you how to cook a pasta in the great way. Giorgio, thank you so much. Okay. Maybe I should do a live here, Giorgio, with you telling me how to cook a pasta. And you will see that you might just give up on me. I'm not very patient with the cooking. I think I'm good at tasting the food. The part about cooking that I really like is tasting the food, you know? But thank you for your suggestion. That is really good to know. So Milan is good for shopping. Okay. I'm not much of a shopper. So I don't really like shopping. Although when I was in Rome, I did get a really nice coat there. Because there were these wonderful ladies who like wanted to dress me, you know? They wanted to like give me the right shoes and dresses and they're like, "You know what? You should wear that coat with that dress and take these shoes off and wear these instead." And then before I know it, I'm spending like a bunch of money on clothes I don't need, but I do want because it's from Italy. So, okay, good to know. Don't go to Milan. You should go to Florence is way better. Oh, Florence. Florence. Nightingale. I sub your channel. Thank you. Please subscribe to my channel. Instagram, Facebook, and YouTube. I watch them every day whenever I am alone in the night. Okay. Hello, Jayanto. Could you speculate on what? Stocks? Yes. Do you want to go out sometime? I do go out most days. Always remember to knock before opening the fridge. Every ethnic has issues. You have a beautiful smile. Thank you, Milo. That guy is like a stalker. Well, don't stalk me. Hmm. So you can't cook. What if you get married? I love masala. Well, I would hope that they know how to cook, whoever I marry. Do you want to go on a date sometime? Um, Spoiled brat. Have you heard of Bocca de Beppo? I have not. Maybe mystery shopper. Are you Southeast Asian? Can we do something about this person, please? Northern Italy is beautiful. Okay, so I'm calling the live dark matter live. They were moving faster than they should. Conundrum. Okay, I think that's a pretty good. I hope one time to go in USA as well. Do you have any suggestion on what to must see in the US? Oh my gosh, yes, you should come to Boston. You should come to Boston and then go to New York. And there are lots of beaches around here. And then you should see the Grand Canyon. It's a direct flight from Boston to Las Vegas, and from Las Vegas you can go on tours to see all the canyons around. And then come back to Boston. You should comment on our Italian food here. There's an entire neighborhood of Italian food here. You should tell them how to really do it. And yeah, that's your itinerary. Yes, I'm in Boston. Mhm. Okay, now let me get my dark matter thumbnail out. Reddit has become a clutter. Can we link? Maybe collab on some restaurants? Sure. You can message me on Instagram. Boston by Augustana is a good song. I do hotel reviews and activities on my TikTok. You could follow me there as well. It's the same handle as here, Oindripi, on Instagram and TikTok. I do travel and hotel videos on there, okay? On my TikTok and a little bit on my Instagram. Who loves me? Hopefully, mommy and daddy, and my children. I don't know. And Jeremy. And you. But don't do anything creepy, guys. Just don't. Hi, David. I hope mommy and daddy love me. Mommy, daddy. You can definitely have multi-dimensional, like more than the 3 dimensions. Oh, thank you. See you next time, Giorgio. Don't go to Miami. I don't think you like it, Giorgio. I don't think you're gonna like Miami. I think you should come to Boston, go to New York City, come back to Boston, try all the Italian food and criticize them, then go to Las Vegas direct flight, take tours to all the canyons, including Grand Canyon. And that is the best thing to see in this continent, probably. We love you too, of course. Thank you, Adam, darling. Oh, shut up. El Hode, don't you joke about that. She's a mom of many babies. You are Jenna. What do you mean, Zivota? What do you mean? What about Deep Texas? No. Leave this Italian alone. I'm speaking to an Italian. Fission or fission? What do you mean? You mean fusion? Ah, Texas is hot and like so big. He'll have to drive and he's from Italy. So let's no, not Texas. Not Texas, not Texas. Is he? I feel like the ones I recommended, Boston to New York. These are like you can use the public transport. There's so many options, Ubers, everything is closed. You can get to the entire New England with trains and short Ubers and stuff. But like Texas is so big, you'd have to drive, and he might not want to drive. And then just fly to Las Vegas, stay in a hotel, and the tours will pick you up at the hotel and take you to the canyons. That's how I would do it. And then come back to Boston and tell our little Italy what they should be doing. Yes, Texas is so hot and huge. Like Texas is like yeah, it's humongous for a tourist. Uh-uh. No, no. Uh, North Pole, I'm good with the polar regions. I like Alaska. I've been to both of the polar regions and I approve. I approve. I approve of the polar regions. I had fun. California, I mean, California has I mean, it's a great coast, though, right? Like it has, although I do think that the best thing about California is the direct flights to Hawaii. But I mean, California has a lot of really nice nature and beauty, but that I feel like that's too much as well. To hit something like really like out of this world, crazy beautiful nature, I think the canyons are like Antelope Canyon, Grand Canyon. I mean, I think those are great, and those you can do out of Las Vegas easily. There are so many tours. So, Lake Tahoe, I need to do that myself. Hello to LA. How are you? Um, what do you mean, wisdom? Wyoming, Rockies. Actually, Wyoming is on my list of the 17 or so states that I have not done yet, and I really want to do all of them. So Wyoming has the mountains. I actually don't know much about Wyoming, but good you told me. Not too many people in Wyoming, right? Um, and Lake Tahoe, I have not done, although I've done California. Mammoth Mountain. Hmm. Nuclear synthesis of stars. Okay. Is there a specific type of elements you're interested in? Like the heavier elements, lighter elements? Which type of nuclear synthesis? Really? You're timing that person out and not the this wisdom is mine person, Adam? This actually made me laugh. It's almost 3 a.m. here as well, my darling. If it makes me laugh, don't time them out. You guys are too much. You're too funny. Oh, God. You guys are too funny. Okay, while I'm here, let me also title the. I think did not title a couple of my lives. Hi, Johns. I've never had quesadillas. I have had quesadillas. I recommend them. In fact, I really I like burritos, like with a lot of food inside. I love quesadillas. In fact, I am quesadilla. Yes, they're good. Mexican food is good. You should try it. I like tacos. I like I like whatchamacall. I really like a breakfast burrito. Oh my God. A breakfast burrito is my thing, man. Okay, what was this last live about again? Oh shit. If she likes dosas, then you know. I do like those sauce. I love breakfast burritos. Like, first thing, just eating a breakfast burrito. Oh my God, I love it. Mm. See you next time. Hi, Pushpinder. Hello, Taco Bell. Dreamy bedroom eyes. Why you ignored my comments? I think I saw it right now. Do you believe in love at first sight? Or should I walk by you again? Well, thank you so much for watching Pushpinder. El Hode got it. Mm, he knows what I'm talking about. You gotta do a super chat, my love. Taco Bell empanadas are definitely addictive. Pour me some milk. Hello. Hello, my lovely people. I'm about to sign off. I'm about to sign off and go to bed, okay? It was lovely seeing everybody. Please join again next time. Hi, Pepe. Thank you, Jeremy. Please do join again next time, okay? Sweetbread, did you share another photo? I'll have to check. Thank you. Thank you for the hugs and kisses. Thank you. Mwah. 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 Look forward to seeing you again. Yes. Oh, Australia. I'll see you next time. Good night and sweet dreams. Rewind. Rewind the live to see the full thing, okay? Mwah. 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 Good night, everybody. Thank you so much for joining and see you next time. And please like and subscribe so that you can see me next time when we go live and whatnot. And come with your questions and hugs and kisses and good night. Bye bye. Love you. Bye bye. Thank you. Let me actually share the live. Thank you. Thank you. Thank you.